Hi, my name is Wentao, and I'm a third-year PhD student in MIT. It's my great pleasure to introduce my paper on group friendliness in dynamic refugee assignment. This is a joint work with my advisors, Freund and Thodoris Lykouris in MIT, and my collaborator, Elisabeth Paulson from HBS, and Stanford IPL, Sturt from UIC. The motivation for this work is the refugee resettlement process. In this year, there are millions of refugees coming into the North America and European countries. Helping them integrate and thrive is a fundamental goal for the government and resettlement agencies. A common way to measure the success of integration is to look at the employment of refugees. And the geographic assignment of incoming refugees to different locations is a key step in the resettlement process that impacts refugees' employment outcome. Ideally, you want to send a case to the location where the case has the highest likelihood of finding a job. There are, however, three challenges to do so. First, you don't know about the employment outcome until you really send the refugee's case to that location. Second, there are limited capacities for each location due to resource constraints. And third, refugees arrive online and there are uncertainties on what kind of refugees will arrive in the future. We can abstract the problem a little bit by considering the following dynamic refugee assignment process. In this process, there are T online arrivals of refugee cases. For simplicity, in this talk, I will assume that each case consists of exactly one person. For a case, it arrives with a set of covariates. Observing the covariates, the resettlement agency selects a location JT for this case. Each location has a pre-specified capacity as J, and the JT needs to still have remaining capacity before the assignment decision. Finally, there is a reward if this case is employed within some time period. In the United States, it is measured in a 3-month period. The status quo approach ignores the employment outcome and simply does something like capacity balancing across locations, or it's like random assignment. A recent line of approaches is to harness the power of machine learning and optimization. These approaches contain two steps. The first step is to train a machine learning model based on historical arrivals covariate and employment outcome. The model can then be used to predict a new case probability of employment in each location using the case on covariate. And the final outcome is denoted by WTJ. Using the predicted score, the objective is then to find an assignment with the highest expected total employment probabilities. That is, the reward is set to be the score between case T and location JT, instead of the future unknown outcome. This problem is reduced to an online matching problem and can be solved efficiently. Indeed, some papers find an up to 50% improvement in the predicted employment score. In our work, however, we argue that the pure optimization approach will naturally raise group friendliness concerns. Consider the following example. There are two groups of people, one from blue land and the other one from orange land. Both have 90 cases. There are also two locations, location A and location B, each with a capacity of 90. A blue land person has scored 0.7 for location A and 0.9 for location B. For orange land people, the scores are 0.1 and 0.2. Under our settings of rewards, the optimal assignment will simply assign all good locations capacities to blue land arrivals, while all arrivals of orange land will be assigned to the worst location, location A. It is clearly unfair for cases from orange land. So, a natural question is whether we are able to seek efficiency while still maintaining some level of group fairness guarantees. And the follow-up question is whether there must be trade-off between efficiency and group fairness, or there is indeed little loss in efficiency to introduce group fairness. The main contribution of our work is to provide a unified framework to operationalize group fairness in dynamic assignment. Specifically, we first established a flexible framework for group fairness that requires a lower bound for the average employment probability of each group. The lower bound benchmark can be based on any offline problem induced by simple rules for a sample path. We do not impose our definition of groups and fairness. Rather, the decisions are up to the policymakers. Second, we propose two algorithms with asymptotically vanishing regret guarantee. We test our algorithm with data from resettlement agencies in the United States and Netherlands. The data show that the additional efficiency loss due to group vanish is indeed relatively small using our algorithms. So, how to incorporate group fairness? To do so, we must first define a fairness rule, i.e., what we mean by group fair. The simplest rule is probably the notion of do no harm. That is, the change in the assignment policy must ensure that no group will be worse off. Specifically, it means that each group performs as good as what they were under the status quo approach. As I mentioned before, the status quo approach is approximately a random assignment. We then want the average score of a group under the new assignment is lower bounded by that under the random assignment. For our simple example, for the blue line people, we have an average score of 0.8. And for orange line people, we have an average score of 0.15. The new assignment must then ensure that the new average scores are lower bounded by 0.8 and 0.15, respectively, for the two groups. Our framework is also flexible enough to capture other fairness rules commonly considered in the literature. The first one is the max-min fairness rule. For this rule, we want to maximize the benefit of the most disadvantaged group, and then use the score as a benchmark. Go back to our example, it corresponds to a benchmark of 0.2 for both groups. The other notion of fairness rules we consider is called proportionally optimized, which builds on ideas from the machine learning community. Basically, we want that each group is as good as if it received its fair share of capacity in each location and optimize based on that. With these rules, we can first check whether pure optimization is group fair. To do so, we use data from collaborating resettlement agencies in Netherlands and United States. The first two rows correspond to Netherlands data, where people are grouped by ages or educational level. The third row is the US data, where cases are grouped by country of origin. The three columns correspond to the three fairness rules I introduced before. We test three assignments: the random assignment, the optimal assignment without fairness constraint, and the bit price algorithm, which solve the optimal assignment in an online fashion. For each block, we consider the unfairness ratio, defined by 1 minus the realized score divided by the target score. So the higher the unfairness ratio is, the more unfair an assignment would be. As we can see, the bars are all pretty high for the maximum rule, and when groups are defined by country of origin. It does verify that group fairness concerns indeed exist for pure optimization. Given that existing methods are not group fair, we want to find methods that are provably efficient and group fair. To do so, we first need a formal model to evaluate algorithms. Specifically, we still have T online arriving refugee cases. For each case, we observe both the score of each location and the group to which this case belongs to. The group is defined by the policymakers and could be ages, educational level, or country of origin, etc. Again, the agency assigns the case to one location subject to the capacity constraint, and the assignment gives a reward of WTJT. In addition to the capacity constraint, we also have an ex-post minimum requirement OG for each group, namely the fairness benchmark. To evaluate the efficiency, we first write out the fairness-based offline problem. The objective is to find a possibly fractional assignment that gives the highest average employment score, subject to two constraints. The first one is the fairness constraint that requires the average score of each group is lower bounded by the benchmark OG. The second constraint is the capacity constraint that requires an assignment for each arrival, and that the total assigned people in one location is no larger than the capacity quota Sj. Based on this problem, we define two notions of regret. Global regret is the difference between the expected optimal score with fairness constraint and the average score under the algorithm's assignment. This regret measures the efficiency of our algorithm. The second regret is the group G regret. It is the minimum of OG and expected OG minus the average score of group G under the assignment. An ideal result is that with high probability, both regrets are nearly zero. And I want to talk a little bit about the minimum term here. Ideally, we want it to be either just OG or expected OG, but this is provably unattainable in our framework. However, depending on fairness rules and the definition of group, this can be quite close. Indeed, in our numerical result, we do not take the minimum. Then, to design an efficient and group fair algorithm, our starting point is to analyze the fairness-based offline problem. For each sample path, we can write out the offline problem and then take the Lagrangian of it. We show that the expected O star can be upper bounded by the quantity here. Mu j is the shadow price, or the opportunity cost of a slot at location j. And lambda g is what we call the group amplifier, which is the shadow price corresponding to the fairness constraint. We can find the optimal shadow price by looking at the tightest upper bound from the Lagrangian relaxation. The exact derivation is not super important. What's important is the amplified bitprice assignment rule induced by the Lagrangian relaxation. Based on the optimal dual variable, for each arrival, ABP calculates an adjusted score, where the initial score is scaled by 1 plus the group amplifier, and then deducted by the opportunity cost. ABP then selects the location that gives the highest adjusted score. The intuition is quite simple. For a group that needs the resources most, i.e. whose lambda g is higher, arrivals of these groups are more likely to be assigned to their good locations, and the score is adjusted based on how good a location could be for a future arrival. A small caveat of this algorithm is that capacity at one location may get depleted at some moment. To address this issue, we assign an arrival to JABP if the location still has remaining capacity. Otherwise, we will assign the arrival by doing load balancing. To summarize a bit, the algorithm first solves the optimal dual variables. It then assigns based on the ABP rule if there is remaining capacity. Otherwise, the case is sent to a location with the highest remaining capacity, which is similar to the status quo approach. We can prove that ABP is efficient and fair. In particular, with high probability, the global regret of ABP is upper bounded by 1 over square root of t, assuming that capacities of locations scale linearly with the number of arrivals. This matches the common practical scenarios for this assumption, because capacities are usually set proportionally to the number of arrivals. The group G regret under ABP has a term that scales as 1 over square root of the group sizes. So for large groups, ABP is quite fair. But if the expected number of arrivals is quite small, then this bound becomes vacuous. So ABP is not fair. We can test ABP using the same data as before. As we can see, when groups are defined by ages or education levels, ABP is much fairer than pure optimization, since all groups are large. However, for country of origin, since there are some small groups, ABP is still not quite fair and could not meet the target. It is nevertheless still better than previous approaches. Okay, so let's try to understand why ABP could fail. The reasons are twofold. First, for our theoretical result, we rely on the concentration of the fairness constraint over the sample path. What we can show is that the difference between expected score of ABP and the requirement OG will have a concentration rate inverse to the group size. Therefore, if the group size is small, the concentration is weak. The second reason lies in the algorithm. For late cases that arrive after good locations have no capacity, we cannot assign them based on AVP. This can hurt small groups a lot. We propose a simple fix to the above two issues, called the conservative bit price control. First, the algorithm introduces greedy steps. For each arrival, we first predict whether the group this arrival belongs to is at the risk of violating the target outcome. If it is, we directly send this arrival to the better location. Otherwise, we follow the AVP rule. Then, to ensure late arrivals can get good spots, we reserve capacity at all locations for each group. Assuming that the greedy assignment gets some epsilon benefit, we show that both the global regret and group G regret of CBP converges like square root of G over T times 1 over epsilon, where G is the number of groups. Comparing with the guarantee of AVP, there is now no dependence on the group sizes. But there will be extra dependence on the number of groups and the greedy benefit. We show using the same data that CBP is group fair across all settings of fairness rules and all group definitions. Then how about the efficiency? In this table, I show that the average ratio of total employment achieved under different algorithms compared to the optimal assignment without fairness constraint. Note that since it is an offline benchmark, it will always have higher efficiency than any online algorithm, even including those with resolving techniques. If we look at the algorithm proposed in this work, we can see their efficiency is fairly high, with less than 5% loss for CBP and less than 4% loss for AVP, compared with the offline benchmark. To summarize a little bit, in this talk, I discussed the group fairness concern in using a pure optimization approach. We propose a flexible framework for group fairness based on minimum requirement and give two algorithms with provably efficient and fairness guarantees. Data from our partner resettlement agency shows small efficiency loss from fairness. There are a few open problems. For example, one may consider intersectional groups, or the case where each case contains more than one person and with group heterogeneous members. Finally, it is curious to see if there will be an efficient algorithm when the fairness rule is defined beyond a lower bound on every score. With that, I will stop here and thank you so much for your attention. Bye.